Okay, so scale diagrams are used to represent objects that are either too big or too small to fit on a piece of paper or on a computer screen or something like that, right? You can't fit a football field on a computer screen or a car, so you need to scale down the diagram, right? Scale diagram has the same proportions as the actual object, right? So same size, same shape, just differently. So here are some scale diagrams here. Here's a layout of a house, garage, guest room, kitchen, etc. Here's an ant, and here's a car. Determining a scale factor given a diagram. So a scale drawing of the NASA Space Shuttle Endeavour is shown to the right. Find the length of the drawing to the nearest tenth of a centimeter. Okay, so I'm going to guess. Not too many of you have a ruler, so I'll give you the measurement. So what you do is you'd sit down, take a ruler, measure this distance, and you would find out that it was 7.1 centimeters. If the scale used to make the drawing is stated as drawing to actual, then state the scale used to make the drawing. You must always include units with the scale. So we would say 7.1 centimeters on the drawing compares to what number on the actual? So 7.1 centimeters is the length of the drawing on the page, and what is the length of the space shuttle in real life? 37.2. 37.2 what? Meters. Okay, so we are comparing centimeters to meters, right? Now you could do that here, but the scale factor is the number that is created from the ratio of two corresponding measurements using the same units for both measurements. Units are never stated with the scale factor. Okay, so you start off by saying, all right, I know that 7.1 centimeters on the drawing represents 37.2 meters in real life. If I'm going to do a scale factor, then we put the drawing. So you want the drawing up top, and you want the actual on the bottom. So 7.1, that's centimeters. What's 37.2 meters if you convert it to centimeters? So 100 centimeters per meter, so we have to multiply. So 3,720 centimeters, right? Now, we don't put units on these now because they're in the same measurement, right? So we got to start off with units because we're saying, well, this many centimeters represents, in real life, 37.2 meters. To get the scale factor, we get them into the same units. So we could have taken the 7.1 centimeters into meters, right, 0.071, but it makes sense to take something up to the units. All right, so this has to be converted to centimeters, right? This one is converted to centimeters. It's determine the scale factor used for the drawing of the shuttle. Okay, so that's okay, or we could say 71. So we'd say 7.1 to 3720 or 71. If you don't want to leave a decimal in there, then you can say, well, multiply both sides by 10. Right, they're in the same units now, so it doesn't matter. And it says 71 units on the diagram, in which case we'll probably be using millimeters, would translate to 37,200 units on the actual. Right, so if I'm using millimeters, then I can use millimeters. If I'm using centimeters, same deal, right? And depending on the scale, or depending on how big the drawing is, okay, it might make sense to measure in millimeters or in centimeters. Often with scale drawings, there's a bar included that shows the relative size of the drawing to actual size. If the bar in the picture of the Clava-Zengi bug shown is 2 millimeters, then how large is the actual bug? Okay, so this is 2 millimeters. That indicates that on the drawing, that length is 2 millimeters. Okay. So what we have to do then is measure the bug. How large is the
the actual.
The ruler.
Yeah.
Pick it up.
So what we do is if we measure the actual line on the paper, the line on the paper is going to be 5 millimeters long, right? So 2 millimeters actual length. There's we'll write this down here. The actual length is 5 millimeters. So the actual length of that line on the paper is 5 millimeters, but it's representing 2 millimeters on the drawing, right? So this actual length is 5 millimeters, represents 2 millimeters on drawing. Okay, so we set up our scale as drawing over actual, right? So 2 over 5. And that is x over, and then we can measure on the diagram the actual length, which is 45 millimeters, okay, or 4.5 centimeters. Okay, you need rulers too. We don't have rulers. We're going to get through this. And so then we got to figure out what x is. So we're going to cross multiply. Okay, so again, remember, this is drawing. Okay, so the bar shown is 2 millimeters, and this is actual. And then this will be drawing, and this will be actual. Okay, so we've got 5x is equal to 2 times 45. And note, we've got same units, right? Same units. Okay, and here as well. So everything's got to be in millimeters. You can't take one and use centimeters and then compare that to millimeters, right? When we get to a scale factor, we have to be in the same units. And then we get x is equal to, so we've got 5x equals 90. And x is 90 divided by 5, which is 16, I think. 18. I never get that one right.
Yeah.
Okay, so 18. So that says that in real life, the bug is 18 millimeters, right? So in real life, the bug is 18 millimeters. Okay. In other words, we're blowing it up, right? We're showing a bigger diagram than, because, you know, they're small, so 18 millimeters isn't that big. So the diagram, to show more detail, has to be blown up, right? So we have to increase the size. So we've made it so that it's 45 millimeters long. Okay, and then we can compare, right? So how large, right? So it's figuring out what the scale factor is and then applying that to a measurement on the drawing. Okay, so drawing to actual, and then on the drawing, and what's the actual. The CBC wants to put its logo on a new billboard outside its offices on Memorial Drive. If the logo looks exactly like the one shown, but is to be 5 meters by 5 meters on the billboard, what scale factor is to be used? Okay, so you would need to measure this, and if you did, you would find this is 2.5 centimeters by 2.5 centimeters. Okay, so that's the drawing. So we need to enlarge it, right, using vector graphics, so you don't actually lose any of the curvature. Those of you that know anything about vector graphics would know that. Okay, I mean, sometimes you ever scaled up something on your computer, you zoom in on a JPEG and it starts to pixelate, right? Okay, so with vector graphics, you don't get that, right? When you zoom out, it fills it in as best it can. Anyways, what have we got? So we've got the created to original, right? So the new one, what we want is the created, let's see, new billboard. So the new billboard over the original is equal to, okay, wow, leads to, so the new billboard is 5 meters. What's 5 meters? 500 centimeters, right? So if the diagram is measured in centimeters, then we need to convert every measurement we have into centimeters, right? You have to have the same units. So you can set up a scale factor. So we go 500 centimeters to 2.5 centimeters. Now, you know, those will cross off, right? Because you've got centimeters divided by centimeters. And that gives you a scale factor of, and if you take 500 divided by 2.5, you get 200 to 1. Okay? And if we can get it as a unit, that's kind of nice, right? It tells you, well, for every 1 unit on the original, you're going to have 200 units in real life, right? So for every centimeter on the original, we're going to have 200 centimeters in real life. Okay, so that's the scale factor. So when we say the scale factor is 200 to 1. Okay. So scale factor is generally expressed as a ratio, and with the ratio you use a colon, right? 200 to 1. And the units have to be the same, right? That's how you can drop the units. Okay. We can't do 5 meters to 2.5 centimeters. Oh, 5 divided by 2.5 is 2, so it's 2 to 1. Wait a sec, it's going to be kind of small then, right? No. So you have to be in the same units. So the big thing with scale diagram, make sure you're measuring in the same units, or convert to. The concert promoters for last night's 1-2-1-2-1-2 concert want to put the logos below on t-shirts. What would be reasonable scale factors for each of the logos? Okay. So if you measure this, you will see that the actual length is 5.7 centimeters. And if you measure this, you will see that that length is 1.3 centimeters. Okay, now this is kind of, I mean, on the whiteboard it's weird, right? Because it's blown up bigger than would fit on a t-shirt, but what you're looking at is on the paper, right? So you're saying on the paper, if we need to enlarge that if I wanted to fit that onto a t-shirt, right? Yes. So you have 5.7 centimeters. You might want to round that, okay, and figure out the width of a t-shirt. And go with, okay, so we're going to enlarge, which means we'll have a bigger number first, right? A large scale factor, and a smaller number second. So you could do, I should have to figure out ruler, how wide is the t-shirt? The t-shirt maybe got about 30 centimeters, so maybe about 24 centimeters to work with.
If this question was on test, you have to measure your shirt.
Well, what we do then is show you a t-shirt in the front of the t-shirt, right? And say, okay, it's like, so if that's 6 centimeters, I got about 24 to work with, then how much bigger can I make it? I can enlarge it by a factor of, take 6 to 24 by a factor of 4, right? So if t-shirt shirt width is about 24 centimeters, then we can enlarge 4 to 1, right? So we take an actual length of 6 centimeters and turn it into a length of 24 centimeters, right? So we're scaling up. If that's 1.3 centimeters, so call that maybe 1.5 centimeters. How many 1.5s are there in 24? So you could do that by taking 24 divided by 1.5. There is a way. 16. Okay, so about 1.5 centimeters.
How do you know it's 4 to 1?
So what we're going to do is take 24 and divide it by 6, right? We're saying, so how many of these would fit into, I can fit 4 of them, right? Well, I don't want that. I want to enlarge it, so then I can enlarge it by a scale factor of 4 to 1. Right? If I make it 4 times as big, it'll fit. Yeah. Now, I mean, depending on the size of the t-shirt too, right? You may increase the logo, like not always print the same logo. If I'm printing like a triple XL or something like that, got a lot more to deal with, right? Oh, thanks for reminding me.
I had this. I had a York peppermint patty, which I stuck in my pocket, which is not a good idea, right? Because then they melt. So then I hung it outside the window. It was cold, so that it would solidify. And I would have forgotten all about it. So there it is, slightly melted.
Yes.
Oh, you!
Thank you.
So the opening window reminded me that, oh yeah, otherwise I would have had a surprise next year. Okay, what was this, 16?
Yeah, it is.
Okay, so 16 to 1. And I don't have a measurement on the who, so. I mean, I guess probably it's how big, in fact. Let's say it's about 3 centimeters. Then what would you enlarge it? You do the math in your head. If this is 3 centimeters, 8 to 1. So, I mean, conceivably, this is a project you could go through in multimedia, right? It's, hey, I've developed this logo. Well, how big is it actually? It's this big. We want to print it on t-shirt transfer paper or whatever, right? Then what do we enlarge it? So you need a scale factor. Making a scale drawing given a scale factor. So if you've got the scale factor you want to draw, then you have to know, well, how big do I make things, right? So a shed is to have a rectangular garage of 5.5 meters by 8 meters. Use a scale factor of 1 to 100 to make a scale drawing of the base. So you say, okay, I need 1 to 100 to be equal to x over 5.5 meters. So 100x is 5.5 meters. X will be 0.055 meters. Now you don't want to measure 0.055 meters on a piece of paper, so what are you going to do with that? Change it to centimeters, right? So you'll get 5.5 centimeters. Okay, so a scale factor of 1 to 100 really would just be kind of converting meters to centimeters, right? It's just I want it to be 1/100. So if it's 5.5 meters, 1/100th of 5.5 meters is 5.5 centimeters. Okay, and then what's the 8 meters going to be? 8 centimeters, right? Okay, so in effect that's what we're doing. So when you go to do that scale of 1 to 100, right? So 1 to 100, because there's no units on there, okay? Because we could have said use the scale factor of 1 meter is 1 centimeter. Grape was close. That was weak.
Crumble it up tight.
Yeah, it's tough to fly. But I think if you threw it flat like that, you might get better aerodynamic.
Right.
That was
Why did you
sad.
arc it?
Ooh.
Ugh, it's too light. Yeah, the grape is heavier.
Scavenging on over.
Sure.
Oh, why would you do that?
Oh,
Oh,
jeez.
Tanner! Oh my God!
Today's not my day.
And when was it we knew Tanner was not destined for pro baseball? It's like a piece of gum and a crumpled up thing.
That's really disappointing.
Thank you. Yeah, I mean, I could read, but not that big. Nice. Okay. In general, if the scale factor is between 0 and 1, the scale diagram is smaller. Okay, so you're looking at that 1/100th, right? The one we just did. 1/100th, the diagram will be smaller than the real life. And if the scale factor is greater than 1, then the scale diagram is bigger, or let's use a fancy word, larger, than the actual object. Anybody make scale models? You know, you see scales like 1/32 or something, right? 1 to 32. Okay. So what does scale factor then do to the area of an object? Okay, what's the area of this rectangle?
48. Beat you to it.
48 what?
Centimeters.
Square centimeters, right?
Oh yeah. Volume is cubed.
So area, yeah, and volume is cubed, right? And we're going to do volume and scale factor too, but we'll save that until tomorrow.
Ooh. Fun stuff for Thursday. Yay.
Fun stuff. We said the easy stuff for
Thursday,
later.
that means half a day left. 1.5 days.
Okay. Okay, so I have filled in the first line for us, right? We're using the original object on the first line. So scale factor of 1, you're not actually changing anything. So the length is 12, the width is 4. The new area, well, same as the old area, the new area is 48. The original area was 48. Okay, and as a matter of fact, the original area is always 48. We can even fill in the rest of the chart for this, right? Because the original area is always 48. The new area over the original area, is actually the scale factor, right? And we're going to look and see what, wow, it's really scale factor squared. And then we're going to multiply that by the original area and see what we got. Okay, if I scale it by a factor of 2, then instead of being 12, it's now 24. And instead of being 4, it's now 8. So what's happened is we have doubled the length, but we have also doubled the width, right? I have to double both. 24 times 8 is 60 and 9, 192. 192 divided by 48 is 4. The scale factor is 2. What's the square of the scale factor? 4. What's this number 4 times the original area? 4 times 48 is? 192.
Wow.
The same numbers are coming up again and again.
It's a miracle. The no money miracle.
Yeah, see, it's free. Okay. 3, scale factor of 3. Okay, was 12, now it's 36. Width was 4, now it's 12. So what do you think is going to happen to the area if I triple this dimension and I triple this dimension? Okay, let's see. So what's new area? 36 times 12 is how much? 432.
32.
There you go.
What's 432 divided by 48? 9. Okay, what's the original scale factor is 3. If I square that, what do I get? 9. And what's 9 times 48?
452.
432. Yeah. Is there some pattern going on here? What kind of reasoning would we be using if we were looking for a pattern? Inductive reasoning. Hey, pretty good. Right? So, lots of people, you're like this far, right? We just gotta get that mark up a little bit, and what have we got left? We got one test, we got a cube, and we got the final. Okay, so there's still plenty of marks to come.
And putting in marks to lose.
Yeah, well, you can work both ways. 12, scale factor of 4? 4, scale factor of 4?
16.
48 and 16. 48 times 16 is 768. 768 divided by 48 is 16. So its area is 16 times larger. What happens when I square the scale factor? I get 16. Is there a coincidence that these numbers are the same? And what's 16 times the original area?
716.
1/2. Scale factor, so it's 12. Now it's,
6.
and it's 4. Now it's,
2.
okay, so we got 4, we got 2. The new area, 4 times 2 is 8. I don't even need your help for that.
So it's 6.
New area divided by the original area is?
Now you need.
Hang on. Wait. You said 6, right? Sorry, wrote down the wrong number.
Yeah, it's 6.
So that's 12. Okay, that's better. 12 divided by 48 is? 1/4. What's the square of 1/2? 1/4. What's a quarter of 48? 12. All right, scale factor of a quarter was 12, now it's?
No.
Was 12, now it's 3. I'm just trying to write that down now. Was 4, now it's?
1.
3 times 1 is?
3.
3 divided by 48 is?
12. No.
It's okay. We'll get there eventually. What's 1/4 squared? And 1/16 of 48 is 3.
Great.
So you can see that we don't necessarily have to go through all of that in order to find the new area, right? We could say, well, we know the original area is 48. If I scale it by a factor of 2, then think about this, right? I'm taking the length, and now I've got 2L. And I'm taking the width, and now I've got 2W. Okay, so if you think about that, I've got 2L times 2W, which is what? 4LW. But LW is the original area, right? Original area. So because you double this and double this, that's why you're getting the square of the scale factor, right? This is times 2, this is times 2. 2 times 2 is 4. When you triple, this is times 3, this is times 3. 3 times 3 is 9. And then you still got the original area, right? L times W. Compare the values in the column labeled new area to the column labeled square factor. Square factor? Yeah. Compare this to this, right? They're the same. Yeah, you could put they the same, because I'm not going to look at your notes. Okay? So if you want to find the new area, you don't have to go through finding what's the new length, what's the new width, right? You just have to square the scale factor and say it's that proportion, right? So if the scale factor squared is 4, then the new area is 4 times the original. The scale factor squared is 1/16, then it's 1/16 of the original. Okay, one more page. Find the area of the circle shown. Note, A equals pi r squared. Okay?
50.3.
So it's 16 times pi.
50.3.
Let's just leave it as 16 times pi. So here's what's going to happen, right? When we do all of these areas, they're always going to have a pi in them. Right? So that then when we divide original area by new area, the pi's will divide out. Right? We're not have to worry about, how do I round this? Yeah. And you won't even be here for Pi Day. March 14th. Complete the table below. So the radius originally is 4. Let's just fill this in going down. So if I scale factor it by 2, what's the new radius? And then, lots of numbers are being thrown out, none of which are actually correct. Okay, so what are we doing in a circle, right? We are only changing one measurement, which is the radius. With a rectangle, we are changing 2 measurements, right? We got a new length, we got a new width. Here, we just have a new radius. But notice what's happening. When you're working out the area, you're squaring the radius, right? You're just multiplying that number by itself. So we only really need to change one number. So if we work out the new area, so what do? We take the radius, we square it, and then we put a pi down. So the new area, well, this was 16 pi. If I square this, what do I get? 64. 12 squared? 16 squared? 2 squared? 1 squared? What was our original area? Well, it was always 16 pi. New divided by original, 16 pi divided by 16 pi is 1. 64 pi divided by 16 pi is 4. Okay, so the pi's are just going to divide out, right? That's why we don't want to have some rounded number. Right, if we just always express the area in terms of, well, something times pi, 144 divided by 16 is 256 divided by 16 is 16 divided by 4 is 16 divided by 1 is, oh, sorry, wait, it's new area. 4 divided by 16 is, and 1 divided by 16 is. Okay, so what do? We just went through a whole pile of inductive reasoning by sitting down and saying, if I do this to the radius of a circle, then I'm going to end up with new area divided by original area is these numbers. If I just square these scale factors, what numbers do I get? The same numbers, right? So we can reason that if the scale factor is double, then the area is double squared, or 2 squared, which is 4. If you triple, scale factor is triple, I make that circle 3 times bigger, its area becomes 9 times bigger. Okay? So area increases with the square of the scale factor. Right? Big thing, that's the takeaway from today. Right, for this lesson. Area increases with the square of the scale factor. Just think about your rectangle. Just say, what did I do? I doubled this and I doubled this, so I've got 2L times 2W, which is 4LW. LW is the original area, so I have 4 times it. If I take 3R, whoops, didn't want to move that. Hang on, let's see if we can. So if I'm tripling, that means I'm taking 3R. When I square that, what's 3R quantity squared? 9R squared, right? So you're going to scale it up by a factor of 9. Anyways. This times the original area, so 16 pi, right? It's just going to be the new area, 64 pi. So this gives you the same as the new area, right? So to find the new area, you can actually triple the radius, right, and get a radius of 12, and then work out the area and get that 144 pi, or you could just say the original area was 16 pi, but I'm scaling by a factor of 3, and I have to, it's an area, so it increases by the square of the scale factor. So multiply by 3 squared and get the 144 pi. Okay. What are these guys? Same. Yep.
How come you don't multiply like 4 times 5?
Where?
Just as an example though, for
So remember, the formula is pi r squared, right? So I want to take the r. So when I said the r was really 3r, I should have done this. And then said this is the original area. So by tripling the radius, we've got 9 times the original area.
okay.
Similar to the rectangle, if you triple it, you now have 3L times 3W, which is 9LW. Determine the area of the trapezoid shown. Okay, so there's actually a formula for area of a trapezoid, which is 1/2 h times a plus b. This is h. So with the trapezoid, the height of the trapezoid is the distance between the parallel lines. Okay, and what is a trapezoid? A trapezoid is a figure that has one pair of parallel lines and then two other lines which aren't parallel. Okay, so if you look at any of the tables in the cafeteria, they're all trapezoids, right? They've got the two edges like this, and then the sides come out, so they have different, they're not parallel. Okay, so using this, we're actually going to have to do a little bit of trig here, right? It's a good review. Make sure your calculator's in degree mode. So I have a 40-degree angle. This is a right angle, right? Because it's a height measured from a flat line. You're going up and down, right? It's perpendicular. What's the name of this side? Opposite. What's the name of this side? Hypotenuse. Which trig ratio do we use? Sine. So we'll say sine theta is opposite over hypotenuse. The sine of 40 degrees is equal to h, which is kind of a weird letter to use because it could be a hypotenuse, but it's height, divided by 7, which is the actual hypotenuse. So h is equal to 7 times the sine of 40 degrees. Now, if I'm doing this on the calculator, and I write out 7 times sine 40, right? 7 times sine. Make sure your calculator's in degrees, 7 times sine 40, and hit enter. You get a number. Okay, that number is going to be, what is that number? 4.5, exactly 4.5?
12.1995.
So, we know at this point that we should only round when? When do we do the rounding? At the end, right? And this is a number that we're going to use in another calculation, which is this one. So we'll say area is 1/2 h. Now a plus b, doesn't matter which one's which. Okay, the h comes from there. Okay, so when you go to work out the area, you go 0.5 times second function answer, or arrow up and bring that number down, right? Depends on the calculator you're using. So 0.5, 1/2, right? Or go bracket 1 divided by 2, times second function answer, times bracket 10 plus 18 bracket. Make sure that's in brackets, right? Because you have to actually get, or just multiply it by 28. Okay, so you might recognize, hey wait, 10 plus 18 is 28. So 0.5 times second function answer times 28, or times bracket 10 plus 18. And then round that, what do we get? Give me 1 decimal. All right, what is it about? So that's 28, that's 14, 14 times 5. 14 times 5, like 70-ish?
Yeah.
62.99?
Oh, the area.
All right, so let's call it 63. Okay, if it's 0.99, we'll just go to the nearest whole number, right? 63 is good. Okay, and notice estimation, right? When I do an estimation, say, okay, it's 1/2. Okay, I know that's, I can use 5 for it, and it's, so it's 1/2. So 1/2, and that's 28, so that's 14 times 5 is 70. Okay, yeah, it wasn't really a 5. So it's lower, but it's in the right ballpark, right? Sometimes you get really weird answers for stuff. Okay, and it's just due to rounding on your calculator or not recognizing what you're doing. Scale factor of 3 is used to draw a new trapezoid. State the new area. Okay, did you learn anything? What's the number? What's the new area?
3 times 6.
Well, didn't learn anything. The scale factor is 3. The area increases by a factor of 9. Okay, so 9 times 63, 567. Okay, so remember what's happening is we're increasing everything by a factor of 3. So this is now 54, and this is 30, so it's 3 times 28, right? That's multiplied by 3. The height is now 3 times what it was, right? That's now 21, but we don't have to go back in and rework it, right? That's the whole point. We don't have to go and draw this diagram and say, well, that's 21, and that's 30, and that's 54. And what's going to happen to the angle? Is that going to be 120? No, the angle's going to stay the same, right? Because it's going to be a similar drawing. Similar means same size, same shape, right? Different size. So the angle's going to be the same, right? But you don't have to sit down and draw this and say, well, this is 21, and that's 40 degrees, and this is 54, and that's 30, and, right? We don't need to do any of that, right? We say, look, I'm scaling it by a factor of 3, so the area scale factor is 3 squared, or 9. Okay, I'll leave this. This would be a linear scale factor, right? Linear scale factor just says the line's going to be 3 times bigger. So that'll be 21 centimeters. That'll be 30 centimeters. That'll be 54 centimeters. That's a linear scale factor. This will be equal to 3h, right? Where the h is the number that was up there. It's going to be 3 times that. But we don't need to draw it all out again and recalculate it. We just say, if I'm scaling it by a factor of 3, then the new area will increase by a factor of 9. Determine the area in square units of the picture below after it is reduced by a scale factor of 30%, enlarged by a scale factor of 200%. So the best thing to do would be just to figure out what's the area as it stands, right? So as we've got it, what's the area? So we have a semicircle. Okay, a semicircle is going to be 1/2 pi r squared. The radius, if we measure it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I think each of these guys here is 1/2 centimeter. So this surface area is 1/2 pi times 5 squared. This is a trapezoid, right? The height is 1, 2, 3, 4 of those. Okay, so the height is, okay, what did we say? 1, 2, 3, 4, 5, 6. So we said each of these was 1/2 centimeter. Okay, so surface area of a trapezoid was 1/2 of the height, which is 2. Oh, sorry, wait a sec. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, wait. The radius is 5. So each of these is 1 centimeter. My bad. That's 10. Each of them is 1 centimeter. Height is 4. And then we've got A plus B. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so every square is supposed to represent 1 centimeter. This surface area is 60. Okay, 10 plus 20 is 30, times 4 is 120, times 1/2 is 60, or 1/2 of 4 is 2, times 30 is 60. That's 12.5 pi, right? 25, 5 squared is 25, 1/2 of that's 12.5, and then we've got the pi. So the total surface area, before any changes, is 60 plus 12.5 pi, which is 99.27 square centimeters. Okay, or if those aren't centimeters, then it's in square units, where a unit is just 1 block. Okay, so I'm going to say they represent centimeters. If you reduce by a scale factor of 30, so this is an important point. If it's 30% smaller than it was, then how big is it? What percent of the original is it?
So okay, right now it's sitting at 100%. If I make it 30% smaller, then what percent is actually left? 70%, right? So reduced by a scale factor of 30%, we got 100% minus 30%, which means we have 70%, or a scale factor of 0.7. Okay, so the scale factor isn't 0.3, right? It's reduced by a scale factor of 30%, which means what's left is a scale factor of 70%. So our scale factor is 0.7. Our area is the square of the scale factor times the original area, 99.27. And let's just call these units. Units squared. Okay, so we'll say this is 1 unit. Okay, however big they actually are, doesn't matter. Okay, so we need 0.7 squared times 99.27, which is, I worked it out. Now, remember, it's not really 99.27, it's really whatever number is sitting in your calculator, right? Because when do we round?
At the end.
At the end.
You just like.
So let's put 3 dots on there, 99.27 ... Okay, and that works out to, now we'll round, 48.64 units squared. Okay, rounded to the nearest term in the area, rounded to the nearest dang it, moved it again.
Wait, how does that make
Round. Oh wait, that's. Can I do that? Rounded to the nearest 100. Enlarged by a scale factor of 200%. So do I multiply it by 200? So scale factor of 200% makes it how many times bigger? 2 times bigger, right? So we got to take 200%, converts to a scale factor of 2, right? Just divide by 100. Change a percent into a decimal, right? So you take 200 divided by 100, which is 2. So what do I multiply by to get the new area? I haven't learned anything yet. If the scale factor is 2, then the area is increased by a factor of 4, right? Square of the scale factor.
Danny, I said that you said we didn't learn anything.
No, it's because somebody else said 2. Which is, rounded 2 decimal places, 397.08 units. Units squared. Okay, so remember, it's got to be square units, right? Because it's area. If we're doing volume, what are the units? Units cubed. Okay, give me a second. You just have to copy that out. So remember, the takeaway is you figure out what the scale factor is, especially if they give you a percent, especially if they reduce it by a percent, right? So just think, I'm going to buy a coat and it's reduced by 30%. It's a $100 coat. I'm paying $70. Right? So you still have 70% left. 70% as a decimal is 0.7. Your scale factor is 0.7. You multiply by the square of the scale factor, which is 0.7 squared, or 0.49, and you'll get the answer. Okay, what do we got? 2 more? Let's go to the end this time, so I don't have to append videos. Good. The area of the inside of a triangle is 4/9 the area, the inside triangle is 4/9 the area of the outside triangle. If the length of the base is 27 centimeters, then determine the length of the base of the outside triangle. Bless you.
Thank you.
Okay, so if that area is 4/9, it's a reduction, and it's reduced by a factor of what? What's the scale factor? So you're given one area compared to another area. And you know that area is the something of the scale factor, so what's the scale factor? So it's a number. Okay, we're partway there. We know it's a number. Okay, I'll bet you it's a number that can be expressed as a fraction, and the fraction is. Okay, so if I apply a scale factor of 1/2 to an object, what does that do to its area? The area scale factor is 1/2 squared, which is 1/4. Okay, so now I'm giving you the area scale factor. The area scale factor is 4/9. What's the linear scale factor? 2/3. What do? You have to take the square root of it. That's somebody new. Okay, linear.
Oh, square root.
Okay, so if you get the area scale factor, you know that the linear scale factor is the square root, right? We're going backwards. So that if the base of the inside triangle is 27 centimeters, then it's 2/3 of the base, right? Because we're dealing with the inside triangle. So this is 27 centimeters, and we know that that's 2/3 of this length, right? So we can say 2/3 of x is equal to 27, right? So I'm scaling down the outside triangle. I'm going to make it 2/3 the size that it was. 2/3 of something is 27. What's the something? How are we going to solve? What's the easy way to solve that? What's the first thing you should do? Multiply by 3 to get rid of the denominator, right? Don't like denominators, let's multiply everything by 3. Gives me 2x is equal to 81. Okay, now it's easy. What's x? 81 divided by 2, or 40.5 centimeters. Okay, so the original takeaway was, if I take a linear object and I scale it, then its area changes by the square of the scale factor. If I'm given the area scale factor, then to work out the linear scale factor, I have to square root it, right? So if I know that the area of that inside triangle is 4/9, that's scaled down, of the original area, then I know that the linear, that object is 2/3 the size of the original triangle. 2/3 squared is 4/9, right? Giving me 4/9. Okay, and then we could just work that out to say 2/3 of some number is 27. And that number is 40.5. Quilt for baby's crib has 18 triangles, each with an area of 120 square centimeters. A matching quilt is to be made for the baby's older sister. If the design is actually the same, but the total area of the new quilt is 3.456 meters squared, then determine the scale factor that can be applied to the dimensions of the baby quilt, so the older sister's quilt. So determine what we're going to work out is the linear scale factor. Write that down quick. It's in thin writing, so it's going to disappear.
Linear.
Then I'll have to rewrite it, and it'll be thick. And I don't know why this happens, but it does. Anybody watching this video knows why it happens, let me know. Okay, so at some point that's going to disappear. So the original quilt, each triangle has an area of 120 square centimeters, matching with design size of the total area of the new quilt. So we have 18 triangles, so the original quilt, it's all going to disappear, come on, disappear already. Original quilt
area is 18 times 120.
Original quote.
Yeah. What's 18? Yeah, the OG. What's 18 times 120? Remember these numbers, because it's all going to disappear. I don't know when.
2,118.
2,160. 2160. There we go.
I just got original quote down.
Okay. So, here's the problem. We have different units, right? We've got 120 centimeters and we've got, 120 square centimeters, which gives us 2,160 square centimeters, but the total area of the new quilt is given in square meters. If I want to work out the area scale factor, which is what we're going to find, right? Because we're going to be comparing two areas, one to another. So we either have to get this into square centimeters or get this into square meters. Which one? Let's take this to square centimeters, right? So what is this? 3.456 meters squared is equal to how many centimeters squared? How do we do that? Okay, how many meters in a centimeter? Okay, so I want to get rid of meters squared. We'll fill that in later. So 1 meter is 100 centimeters. Now if I cross off this m, I just cross off the square. So I still got an m, so I got to multiply by another 100 centimeters is 1 meter. Now I cross that off. And I'm left with centimeters times centimeters, which is centimeters squared. Okay, so how many square centimeters is this? One, 2, 3. So you're gonna multiply by 10 to the 4th, right? So you gotta move the decimal over 4 places. So after the 4, the 5, the 6, then you gotta put a 0 in there. So it's 34,560 square centimeters is the original, right? You're not just multiplying this by 10, or sorry, by 100 to turn it into square centimeters, right? That would only turn one of the dimensions into centimeters, right? So we've got so many meters by so many meters. So we multiply by 100, and then another 100, so we get meters times meters is meters squared. So you gotta watch for that when you're changing areas around. Okay, so the area scale factor is this. The area scale factor is 34560 divided by 2160, which is equal to what number? We're doing 34560 divided by 2160. 16. So the area scale factor is 16. What's the linear scale factor? Hold up the right number of fingers or say the number. So if the area scale factor is 16, what's the linear scale factor? 4, right? Square root of 16. And that's what they were asking for, right? They weren't asking for the dimensions or anything. They're just saying, what's the linear scale factor? In conclusion, some important formulas you will need to know. They can be found on page 475 of the textbook. If the dimensions of a 2D shape are multiplied by a scale factor of k, this is a linear scale factor, right? In other words, it's just making lines longer or shorter. Then the area of the scaled shape is k squared times the original shape, or k squared is equal to, you're going to take this divided by this, right? The area of the scaled shape divided by the area of the original shape. Right? So in this last one, we had to do a number of things, right? We got to figure out the original area of the quilt. We got to take the area of the new quilt, but change it into the same units. You can't get a scale factor if the units are different. Took the new divided by the original to get the area scale factor, saying this is 16 times larger in area, which means that each dimension is 4 times larger. The linear scale factor is 4. Fade to gray.